Hey, welcome to Ones and Zeros. My name's Ben, and today we are taking a look at another episode in our STM32 basic series. In this episode, we're going to be taking a bit of a look at low power modes with STM32 devices, which are things that are particularly handy in situations where you may not need the CPU to be processing data all the time, or in situations where you may be running a system off battery and you want to be able to conserve power, things like that. And particularly is something that we're going to be using in the upcoming series where we're going to be looking at building a bit of a brain for a robot that will be running on battery. So there's three main low power modes that you've got when you're dealing with most of the STM32 family. And those will give you a different amount of power saving depending on which mode you go into, and depending on which mode you go into will depend on how much of the actual system inside the chip gets turned off while it's in that low power mode. I'll also take a bit of a look at the different ways that you go about actually waking the device back up again, and we'll also see what the current consumption is of the device while it's in different low power modes versus when it's actually running. So we're going to be using the typical STM32 F411 Nucleo board that we've used for a lot of the videos in this series. And this one also allows us to be able to hook up a multimeter so that we can measure the current consumption as well. But before we get into that, let's have a bit of a look at the actual low power modes that we have available. So we will jump over to our screen, and we've got the Quartz Arc code sitting here at the moment that is available up on GitHub, which we'll have a link to in the video description as well. But if we bring this one over onto this screen, we can have a look at the three low power modes that we've got available on this particular device, which is the STM32 F411. So as we can see, we've got our sleep mode, our stop mode, and our standby mode. And depending on which one of those modes we go into determines how much of the chip actually gets turned off. So we can see in the sleep mode, we have the ability to be able to wake up by interrupt or by a wake up event. That mode turns off the CPU clock, but it keeps all of the other clocks and the analog clock sources running. So it's our least deep sleep mode and leaves more of the system running than the other two modes. It's also the easiest mode to come back out of, because when we come out of the sleep mode, it allows us to basically just keep running code from the point where we actually went into the sleep mode. So it's quite a handy one, but it also consumes more power than if we're in a stop or a standby mode. If we have a look at the stop mode, we can see that it's turning all of the 1.2 volt domain clocks off. The HSI and HSE oscillators are turned off, and the depending on the device, depends on which regulator it's actually going to be using. Different devices have different options available there. Our deepest sleep mode is our standby mode, and in the case of that one, it's basically turning most of the device off, including the voltage regulator, as well as all of our clocks and oscillators and things like that. So with the standby mode, we have to do more work to bring the device out of sleep than we would if we just went into the normal sleep mode. So we'll take a bit of a look at how that works with the code. So like I said, with our normal sleep mode, the first one in the list, that allows us to basically just come back in and keep running code. If we go into the stop mode, we do have to do a little bit of work to get back up and running when we come out of the stop mode. And with the standby mode, when we come out of that one, it's basically starting the chip from scratch. So it's basically booting it from scratch in that event. So we'll have a bit of a look at how those work. So let's get some code written. We've got the code here from the last video that we did in the series. And if you do want to go back and see some of the previous things that we've done, because we change up the code with each episode in the series. There is an option in GitHub, which I'm going to do a little bit of a video on, where you can actually sort of roll back and see previous versions of the code as well, which allows you to get a bit of an idea of the sort of the demonstrations and things that we've done in the older videos as well. So in this case, let's get rid of the stuff that we had here from that video. And just at the end of our initialization code and before we go into our processing loop, we're going to pop a bit of code in here. So let's have a look at our sleep mode to start off with. So let's chuck a bit of a comment in here with a few details about what we're actually doing. So in this case, we're going to be waking from an event, which will be triggered from the user button, which is connected to pin C13 in this particular instance. We're going to get it to print a little bit of info out to serial so that we can see that it is actually going to sleep at that point. We'll set up our GPIO. Excuse me, losing my voice already. It's been a while since I've done a video. So just setting up at the GPIO for pin C13. In this case, we're setting it up to trigger an event, and it'll do that when the signal is falling, so when we actually push the button. So with that button, we're typically getting a binary 1 or a high signal from that when we're not pushing it, and we get a 0 or a low signal when we do push it. So we're going to be triggering that on the falling edge, so just as we push the button. And we don't need to pull up or pull down or anything like that. The board does actually have a pull-up resistor built in to the circuit. And the other thing that we're going to do for this one is suspend our system tick, because otherwise the system tick will wake the device back up. So we have to turn that one off prior to entering into our sleep mode. And then we can go through and tell the device to actually go to sleep just by using the enter sleep mode function there. Telling it to keep the main regulator on, and that we're going to be using wake from event to wake the device back up from that one. So at that point, the device will actually go to sleep and will be in that sleep mode until we trigger that event using the push button. So in here, this will be when the device is asleep. And then once that event is triggered, it's going to continue resuming code straight from after that. We don't have to do any additional work other than telling it to resume the system tick, so that we've got there to be able to time our processing loop and things like that. And we'll also go through and deinitialize that GPIO at that point and print out a bit of text just to say that we're waking up from the sleep mode at that point. So it's fairly simple to be able to make that work, not much that we have to do. The main things being making sure that our event is going to be triggered, again suspending our system tick, putting it into the sleep mode, and then just resuming the system tick when we come back out of that. If we wanted to continue to use that push button on that particular GPIO, we don't necessarily have to do the deinitialization of the GPIO. It's just it kind of tidies things up again after we've come out of sleep in this particular example. So that's pretty much all we have to do for that particular example. So we're going to build that project. We will get our device plugged in, and we'll get our serial monitor set up and ready to go for that. So we'll just get our cable plugged in for that one. Actually, prior to doing that, let's get a multimeter set up. And we're just using one of my cheap multimeters today. Don't need anything super advanced for this, and hopefully we'll be able to see that screen okay. So I've just got the multimeter leads hooked up to a couple of these little adapters that give us the DuPont connectors. Hopefully we can see those there, which we can then hook up to the board. And if we have a bit of a look at the board, we've got a little jumper here, which is labeled IDD. In this case, it is jumper 6. And we can actually remove that one, and that one's there so that we can actually hook a multimeter up to those 2 pins and allow us to take a current measurement of the usage of the STM32 chip. So got that connected, get the cable connected up to that one, and we're just going to pop our multimeter into, where are we, DC milliamps, somewhere here. And we'll go for our 200 milliamp range. Everything's all connected there. We should be able to see that okay on the screen. And for some reason, it doesn't look like we're actually consuming any current from that one. So let's just check and see that our chip is actually powering up. We'll bring up our serial monitor. And let's just reset our chip. And it doesn't look like it is actually powering up for us. So let's dump that code onto the chip. Okay, and for some reason it does not want to power up. So obviously got something not wired up correctly here. Let's see if it will. Okay, so it's powering up okay now. Figure out why it doesn't want to behave for us. Let's pop this code on there. You can see the little light flashing while it programs. And that one has gone to sleep because we can see the LED is not flashing there. Then if we push the user button, we can see it has actually woken up. So the code is actually working correctly. So let's see if we can get it to actually work for us. And we'll just take that jumper off. Hook our multimeter probes up. That's a bit better. All right. So the device has straight away gone into sleep mode, which is what we want it to do. And if we press the user button, it wakes up and we can see that our current measurement jumps up on the multimeter there. So if we reset that, we can see it goes into the sleep mode and currently drawing about 5.1 milliamps. If we press the user button, it comes back out of sleep mode. We've got our LED flashing and we're drawing, depending on whether the LED is on or off, somewhere between about 17 to 20 milliamps. So you can see that the LED is actually drawing a few milliamps just on its own. So about 17 milliamps without the LED on, and it jumps up to about 19.5, 20 milliamps when the LED comes on. So we can see there quite a bit of savings when we're in the sleep mode, because we're consuming about a quarter of the power that we would be if the device is actually running. And as soon as it comes out of sleep, it just continues to process the code just as we wanted it to. So if we jump over to our screen, and we'll just reset that again, we can see that comes up with a message saying that it's booting and that it's going to sleep. And again, we'll press the user button to trigger that event to wake it up, and we can see that it's showing us that it has woken up. So really easy to use, just the normal sleep mode, not a lot that we actually have to do to be able to make that work, which is really cool. So now that we've had a bit of a look at that one, let's have a look at what we would need to do to get it to do that same sleep mode, but instead of waking from an event, we want to try getting it to wake from an interrupt, which is the other option that we have with that one. So let's jump back to this one here. Sorry, just checking everything's actually working correctly. So we can see in the documentation in our sleep mode, we've tried the wake from event. We're now going to see if we can get the wake from interrupt to work with that sleep mode as well, which can be triggered by any interrupt in the system. So you can have a peripheral or something like a timer, something like that, that's going to trigger an interrupt and actually get that to wake the device up after a particular amount of time, which can be really useful as well. So allows you to be able to wake the device from, say, an external event or from an internal peripheral, different options there. So you could even have, say, interrupt triggered by one of the communications peripherals, so that when it like receives data from an external source, so like a UART or SPI device, something like that, then it can actually wake the device in that event as well. So let's jump into here, and I'm going to comment this code out. So we'll leave it in there so that if you want to grab the code from GitHub, you'll be able to have a look at the various different examples that we'll have in here. And let's get this one in here. Again, just pop a bit of a comment in just to break this up a bit so we can see the different approaches that we're taking here. And again, just going to print some stuff out via serial, and in this case we're still going to use the user button, but we're just going to use a external interrupt connected to that button rather than getting it to trigger an event. So in this case we're going to use the interrupt falling mode for that one rather than our event falling mode that we used previously. And we'll go through and actually set up our actual interrupt like so, setting our priority for that one and the particular interrupt that we're getting set up. So in this case, external interrupt 15 through to 10, because we're using pin 13. And again, for this one, we're going to suspend the system tick so that it doesn't wake the device up, and get it to enter sleep mode. In this case, just telling it to use wake from interrupt instead of the wake from event that we used previously. So again, at that point, the device will be asleep. And similar to before, bringing it back out of sleep, we're basically just going to have to re-enable our system tick, and then we'll disable that interrupt. We'll go through and deinitialize that pin, and then we'll print out a message to say that we've actually woken up. And then the other thing that we want to do for this one, because we're actually triggering an interrupt, is we want to make sure that we've got an interrupt handler in there so that we can actually go through and clear that interrupt flag. So we'll open up our handlers files, which is where we keep the interrupt handlers, and we're going to pop one in here for this particular interrupt handler, which is XD15_10_IRQ handler, like so. Grab that one, jump into our CPP file, and I might actually just copy and paste this one just to make it a little bit easier, like so. Won't worry about it printing out message out, and basically all this is going to do is just check to see that that interrupt flag has been set, and then clear it so that it's not going to re-trigger. So again, fairly simple, just a little bit more of actually setting up that interrupt handler compared to doing the wake from event, but it's going to do basically the same thing for us. We will compile that, grab some coffee while that's happening. That's compiled okay. Let's pop that over onto our device. Jump over to that camera again. And we can see that it jumped up and then went back down to about 5.3, 5.2 milliamps, much like it did before. So if we reset that again, see it jumps up to about 22 milliamps, and then once it goes to sleep, back down to about 5.4, 5.5. And then if we press the button, again, that'll bring it out of the interrupt and we'll jump back up to that higher level. Now, we are consuming a little bit more power than we were previously, and that's probably down to the fact that we are using a bit of a cheap multimeter. We're not after 100% accuracy out of this, it's just as a bit of an example. Unfortunately, my good multimeters are slightly busy at the moment, but this one will give us a bit of an idea anyway. So again, put it into the sleep mode when it resets and press the button to bring it back out, and away we go. So that's our normal sleep modes, like so. Jump back over to our screen, and that's how we go about using both wake from event and wake from interrupt with those ones. So the next mode that we've got is our stop mode, as we can see in our documentation here. And with this one, we do also have the ability to do a wake from event and a wake from interrupt. Similar sort of process as what we've used previously. So we'll only have a look at the wake from event in this case, because again, to do the wake from interrupt is very similar to what we were just looking at. So rather than making you watch both of those options, we're just going to go with one of those. I'll just comment this code out. And let's have a look at this one. Again, I'm just going to pop some comments in there just so that we can break that up. And copy our code over for this one. Like so. And much like before, just putting out a message on serial just so that we can see what's actually going on there. Again, we're going to be using the user button to trigger the wake up via an event. So just going and setting that up, much as we did for the other examples. With this one, we don't actually have to go through and turn off the systic, because we're going to be turning off the clocks in the system anyway. So we don't actually have to worry about turning that off, because when the clocks get turned off, the system tick timer is also going to be disabled. So we don't have to worry about that in that case. And telling it to enter the stop mode. Now the thing is because it is actually turning off all of the clocks in this case, when we start up again, although it's going to continue to execute code from this point forward, so we'll be asleep in this point here. Put devices in stop mode so that we don't get it confused with the normal sleep mode. So because the clocks are disabled, we do actually have to go through and set the clocks back up again prior to continuing to execute code to make sure that all our clocks are running at the particular speeds that we want them running at. So we're just going to go through and call our system initialize method, which is in our boot.cpp file. And that will go through and set our clocks up again, much as we do when we actually boot the device in the beginning here anyway. So that way, once we've run system initialize, we know that our clocks are back to the particular speeds that we wanted them running at. And we'll deinitialize our GPIO and then just print out a message saying that we've woken the device up again. So again, we'll just compile this one. And we'll pop this over onto our device. Jump over to that camera. And we can see that it has uploaded the code. It's gone into the stop mode. We did get that message up on the serial monitor. And we can see now that where we were consuming about 5.5 milliamps before in the sleep mode, at the current point in time, we're consuming about 1.5 milliamps in the stop mode with all of the clocks turned off and with the 1.2 volt domain turned off inside the chip. If we hit our user button, we can see that the device has woken up again. And again, we go back to consuming the typical amount of power for the way the device is set up at the moment. You will see more current consumption when it's running, depending on which peripherals and things you've actually got enabled. So because we're not using that many peripherals at the moment, I'm just using one of the UARTs and the system tick and a few other bits and pieces there, not consuming that much power. But if we had a whole bunch of the different peripherals enabled, we'd likely be consuming more power. So that's why it's handy being able to connect the multimeter up and get an idea of current consumption. So if we jump over to our screen, this one here, we'll just restart the device and we can see serial monitor showing that the device is booted. It's gone into the stop mode. And in this case, we can see we're actually consuming very little power. And press the button, it shows us in the serial monitor that it's woken up and the current consumption has jumped back up to the normal level when it's running. So that's our stop mode. And again, you can do the wake from event or wake from interrupt with that one, as I mentioned. Doing the wake from interrupt is basically the same, with the only difference being that we would set our GPIO up in interrupt mode and tell it to use WFI instead of WFE in this particular function here when we call that. So again, the stop mode, you can use different interrupts to be able to trigger that as well. You do have to be aware that because of the fact that it's turning off all of the clocks in the 1.2 volt domain, you're going to be limited in what interrupts can actually wake the device up. And that's why we see here that any external interrupt line can be used to be able to trigger that. So the last mode that we're going to have a look at is our standby mode. And this one is similar to our stop mode, except it is actually turning off the voltage regulator as well. And the main difference with this one, as opposed to the other two modes, is whereas with the other modes, when we wake it up, it continues executing code from the point that we were up to. When we do the standby mode, the device will actually reboot when it wakes up. So effectively, we need to be able to check whether or not it is booting up from scratch, from when we're actually turning it on in the first place, or if it's actually waking up from the standby mode. It's handy to know which one of those is happening, and we'll have a look at how we can sort of tell that as well. So let's comment out code for this one. And again, we'll pop in a bit of a comment in here to break this one up. Now, with this one, we are going to be using a different pin to be able to wake this one up from standby, which means that we're going to need to wire that one up to our actual device in order to make that work. So if we grab what we need to be able to wire that one up. That will do. So what we're going to use in this case is we've got a rotary encoder here. I don't have just a normal push button handy at the moment, but the rotary encoder has a push button built in that we can use for this, so we can just wire that one up. And in this case, we want to supply it with power and ground. And it looks like we've got a dodgy connector here, but this should still work fine for us. So that can be our power, our ground, and wire up our switch there. We'll unplug the board. We'll rewire this one up just to make sure that we're being nice and safe with this. Wire up to our 3.3 volts and a ground pin there. And then we need to find, well, just chuck that all over the place. Need to find pin A1 for this one. Just grab the little chart that has the pinouts for this one. Always try and keep the little chart handy that comes with the device when you buy it. So A1 will actually be this pin right here. So, assuming that we've got that connected up properly, this should work for us. We'll plug that one back in. And we'll copy the code across for this one. Just jump back over to the screen here. Grab that one. And might help if I copy that before I try pasting it. Okay, so in this one, what we're doing is we're first going to go through and actually check this particular power flag to see if there has been a wake up event triggered. So in this case, if it's not a wake up event, then we're going to go through and assume that the device is booting from scratch. So we'll go through and just print out the message like we've done for the other couple of examples. We'll disable our wake up pin just to make sure it's definitely disabled. We'll clear the wake up flag just to make sure that it definitely is cleared. We'll enable the wake up pin and then we'll tell it to go into standby. Assuming that the wake up flag is actually set, then we're going to jump down to this bit of code, which is when the device is actually waking up, and we're going to disable the wake up pin and print out a message to say that the device has woken up. So again, when we go into standby, when we come back out of standby, to be more correct, it's basically going to boot the device from scratch. So whereas we had to go through and run system initialize to do our clocks, we don't have to do that specifically here in this case, because it's going to do that anyway as it goes through and boots the device from the start of main goes through and does the system initialize and gets all of our peripherals set up the way we want there anyway. So let's compile that and pop that over onto the device. Save that one. Jump back over to this one. And wait for that code to pop on there for us. So we can see the multimeter did jump up to the normal level around 20 milliamps there, and then when it went into standby, we've now got 0.0 there. So if we turn this down, we can see we're currently consuming about 0.002 of a milliamp, so consuming very, very little power in our standby mode. Doesn't want to come back out of standby, however, so we may have wired this up incorrectly. Let's just double check that one. And we've actually hooked it up to the wrong pin. So it's wake up pin 1, but it's actually on A0, which will be that one there. So as soon as we plug that in, it's come back up. So now wake up will actually be triggered when we have a high signal. So I'm just going to hold down the button for the moment while we restart the device. That'll go into standby mode, and as soon as I release the button, it'll get the wake up signal and wake back up and go back up to its normal power consumption. So if you want absolute minimum power consumption in a low power mode, standby is the way to go. But there is those couple of things to be aware of. The fact that it will completely reboot when it comes out of standby, and that if you want to be able to tell the difference in between the cold boot and actually waking up, then you do need to go through and actually check that wake up flag to make sure of that one. And again, just so that we can see what's going on there, let's pull up our serial monitor. Just having a complaint at us because we disconnected the device. Just reconnect that one. We'll restart the device. You can see it's gone into standby, and as soon as I let go of the button, it boots up again and then shows it that has actually woken up. So that's how the low power modes work. Again, if you're building a battery powered device or something like that, can be super handy, or even if you're using a device that might run off mains power or something like that, it can be incredibly handy for making a device that consumes minimal amount of power. So when we start the series where we look at developing the brain for the robot that we had a look at in the previous update video, that will be something that we'll be using for the various different STM32 devices, so that we can actually put it to sleep and be able to wake it up. And depending on what we're doing, we may actually use multiple of the low power modes. So hopefully you found that useful. They're quite easy to use, just sort of helps to have a bit of an understanding of what is and what isn't getting changed when you go into those different modes, and how they actually come back out of those modes, the different ways that you can actually go about waking them up. So in the case of the sleep and the stop modes, the fact that you can wake them from an event. With the sleep mode, you can wake it from basically any interrupt, so from any of the peripherals, because those clocks will remain running. Whereas if we want to wake from an interrupt with the stop mode, we can only do that from the external interrupts, because it does stop the clocks for all of the peripherals. And then we need to make sure that we reinitialize the system clocks when we come out of stop, versus our standby mode, where it will actually do a full reboot when it comes out of standby mode. And as you saw, we've got various different amounts of current that will be consumed depending on which mode we go into. So we saw about 5 to 5.5 milliamps for the sleep mode, less power again from our stop mode, and very, very little power being consumed when we go into standby. So depending on what your use case is, there's different options there. So that's those. Thank you to all of those that have been really patient, considering it has actually been quite a while since I've produced videos, having moved house and life just getting a little bit crazy and in the way has sort of prevented videos coming out. So thank you to all of the people that have been continuing to support the channel and all of the new subscribers. We're now over 400 subscribers, which is really awesome. And thank you to our 4 patrons of the channel who have continued to support the channel over that period. That is really amazing that you guys are helping out. And if you like the video, click like. If you're not subscribed and this is the sort of thing you find interesting, definitely hit subscribe. If you want to have a look at the code from this video, we do have our GitHub. I will also put a link to the GitHub repository on the comments below the video. And if you do have any questions or anything like that, we do have the subreddit, or you can send me an email as well, or leave a comment under the video, and I'll try and get to that one as soon as I get a chance. So hope you're having a great day or night, morning, evening, whatever it is where you are in your part of the world, and thanks for watching.